Hello, welcome to this video office hour in preparation for the exam. Thank you for all of you who sent me your questions by email, and I will do my best to answer them. And I'll try to do this in a logical order. So the first question is, how do characteristics like branching, molecular weight, density of side chains, density of chain ends influence free volume and lower the glass transition temperature? Okay, so the key thing to understand here is that as we have a polymer, a block of solid polymer, the more branching that comes off of the main chain and the more density of chain ends we have, so the greater the polydispersity, the greater the dispersity, and the lower the molecular weight, the greater the chain end density we'll have, the more volume we have around the chain ends, because the other polymer molecules can't pack as efficiently around them, the more mobile the chains will be within the solid film, and therefore the lower the glass transition temperature. So let's think about this. Branching, and low molecular weight, and low molecular weight and high dispersity, or sometimes polydispersity index. How do these characteristics influence the properties? And it all comes down to their effect on the free volume. And the greater the free volume, the lower the TG, so there's less of an activation energy required in order to get two polymer chains in the amorphous domains to slide past each other, where the polymer material goes from a glassy state to a rubbery state as you increase the temperature past TG. So with a lower TG, you also have a lower density, and also a lower strength and modulus. And we'll talk about these things more later on in the course when we talk about thermomechanical properties. But the key thing is that these characteristics produce void space in a solid film where the polymer molecules can't quite pack efficiently. That is, there's more space to accommodate polymer chains as the film deforms. So for example, is it easier to pack something where all of the chains are the same length, or is it easier to pack something where you have branches? You know, clearly this is easier to pack. This has more free volume in it. Similarly, if you have polymer chains that are all different sizes, this doesn't pack as efficiently, and you have free volume in all of these places in the vicinities around the chain ends where they can't pack like logs can pack in the back of a truck. How about the difference between the glass transition temperature and the melting temperature? The simplest way to think about a polymer sample is that it has two types of domains in it. It has crystalline domains, or some materials have crystalline domains, not all, and it has amorphous domains. The crystalline domains have a melting temperature, and the amorphous domains have a glass transition temperature. The glass transition temperature is when the amorphous domains kind of melt, but it's not called melting. It's when they become soft. But when the crystalline domains are raised above their Tm, then they melt. So above Tg and Tm, this whole thing is just a viscous liquid. In order to have crystallites, so this is semicrystalline. In order to have crystallites, you need to have repeating order in the polymer chain. You need to have order in the chain. If your material is totally random, like in atactic polystyrene or in an atactic polyolefin, then you don't get semicrystalline behavior. You get totally amorphous. Totally amorphous. And this would be something like a polyolefin where the X groups point whichever way they want. This is an equivalent way of saying, an equivalent way of drawing this is, let me make sure they line up so I don't confuse anybody. This, where this can either be a wavy line here, which indicates randomness, or even a straight line indicates randomness. Now that is differentiated from the case where you have all of the X groups pointing in the same direction. And this is called isotactic. Or in the case where they point in opposite directions but alternating, this is called syndiotactic. Now, because you have regularity here, you're allowed to have crystallites. So if there's regularity, you can have the opportunity for crystallites. If there is randomness, then you don't get crystallites, you get a completely amorphous material. So no Tm here, only a Tg. Okay. I was about to ask if there were any questions, but then I realized I can't see you through the camera. You can send me an email. Okay, the next question is to keep all the variables straight in the, or to clarify what the variables are particularly as it pertains to the Carruthers equation and the Flory distribution. So keeping the variables straight, lowercase p is the extent of reaction, and it is the fraction of reacted A or B functional groups. So 100, or I'm sorry, so 1.00 is would give you 100% reaction. Okay, X sub n is the number average degree of polymerization. The number average degree of polymerization is related to the extent of reaction by the Carruthers equation. X sub n equals 1 over 1 minus p. This is the Carruthers equation. And the number average degree of polymerization is different from X without the n, which is the absolute degree of polymerization for a given population of polymer chains with degree of polymerization X. So it's the absolute degree of polymerization for a given population of chains. So a monomer has x equals 1. Dimer has x equals 2. Trimer has x equals 3. X equals 100 is 100 mer. But if you had two samples, one with x equals 100 and another with x equals 50, x sub n for that whole sample would be 75 because it's the average of the two. At the very beginning of class, we talked about molecular weight and the difference between m sub n and m sub w. And in those calculations, we used I as the index because we always use I when we do summations. I is equivalent to x here. It's the absolute degree of polymerization for that population of which we are speaking. N sub x is the total number of chains in the system with degree of polymerization x. So it's the number of chains in the system with degree of polymerization x. Therefore, x times n sub x is the total number of monomer units incorporated into polymer chains with degree of polymerization x. The total number of monomer units, monomer residues incorporated into chains with degree of polymerization x. So if we have a number, if we have 10 chains with 10, we have 10 different chains with 10 units each, then x times n sub x is 100. So 100 total monomer units incorporated into chains with degree of polymerization x. One more. X times n sub x over n naught, where n naught is the total number of monomer units initially present. So this whole expression then, x times n sub x over n naught, gives you the fraction of monomers incorporated into chains with length or degree of polymerization x. So this is the fraction of monomers in chains with length or degree of polymerization with length x. This is also equivalent to the weight fraction of x of x mers, because we have the total number of monomer units in units in chains with length x divided by the total number of monomer units in the system, which we added at the very beginning of the reaction. Okay. The next question is asking for a bit more detail on what is happening between the nucleophiles and electrophiles in a polycondensation reaction. So this is an amine, this is an alcohol, this is a carboxylic acid, and this is an acid chloride. Sometimes these are called nucleophiles, and these are called electrophiles. And together, when you add these together, you get linkages, either amides or esters. But let's see what happens. You're not responsible for this for the exam, but the question is what is going on in a little more detail. Well, if you see the lone pair here, what happens is that this lone pair, just say if the amine is acting with is reacting with the acid chloride, then this set of electrons goes up here because we can only ever have 4 bonds to a carbon atom. And then the next thing that you get is the electrons go up here to form this minus. And we have the chlorine hanging out here. Now, what do we know about chlorine? Chlorine is a good leaving group because we know that it's stable as Cl minus. So what happens is that this guy, which is called a tetrahedral intermediate, is unstable and it collapses down to give you NH2 plus with the reformation of the carbonyl double bond plus Cl minus, which floats away. Now, usually in this reaction, you need some kind of base hanging around, and the base takes off this proton, and the electrons satisfy that charge, and then you get the amide. And all of these carbonyl substitution reactions work pretty much the same way. But you don't need to know any arrow pushing or anything for the exam. This is just what's going on. Okay, the next question is about temperature effects on reaction rate constants. So a reaction rate constant increases with temperature. So the question is, do reaction rate constants increase with temperature? The answer is yes. How about equilibrium constants? Do equilibrium constants change with temperature? Yes, but it depends on whether or not the equilibrium constant increases or decreases depends on whether the reaction is exothermic or endothermic. If it's exothermic, then the reaction will shift toward the products, and if it's endothermic, the reaction equilibrium will shift toward. Will shift toward the reactants, and if it's endothermic, the equilibrium constant will shift toward the products. Let's see. So we were talking about the reaction between a diol and a diacid. So specifically, take this diol. We don't really care what's in the middle. And we add these things together, and there's a polyesterification reaction that happens. And to get this, this reaction to go, we need to lose 2 H2O molecules. Now, I told you that in order to get high molecular weights, you needed to do this reaction under heat and pressure. Usually it's done in a vacuum oven, in a laboratory scale synthesis. You do it in a vac oven with the heat cranked, and you put a high vac with a water trap to trap the water. Now, even though this reaction is exothermic, and one would think that if you added heat to this reaction, you would shift the product, or you'd shift the reaction back over here. The real reason we add the heat is to help drive off the water vapor, which bubbles off, and that's trapped under in the vacuum, or that's trapped by the vacuum pump. So the reason for the heat, we don't want to just heat this up in the presence of water. The purpose of the heat is to increase the vapor pressure of the H2O, which we're going to remove from the reaction as it's formed. And by removing the water, we're going to shift this equilibrium to the right and increase the molecular weight. So the main point of doing this is not to add heat, because adding heat might cause it to go this way, but to remove the water. Okay, the next question is, can you tell if something was made by step growth or chain growth just by looking at the product? For the purposes of exam 1, yes, but in general, that's half true. So for the purposes of exam 1, anything that looks like this, where these bonds can be bonded to anything, this is almost always chain growth. However, if we have something that has C double bond O and something in the backbone other than carbon, and maybe C double bond O and something in the backbone other than carbon, we'll just say it's X. Then this, so far in the class, this has all been step growth. You could also so this was derived probably from, say, an AB type monomer, where we've shown two repeat units in here, but you could also envision it being derived from an AA and BB type monomer. And the way you can tell is because this group here is flipped. So this is derived from something with X's at the end, and then this piece, which continues over here, was derived with something with either an acid or an acid chloride at the end. So this would also have been step. But is this true in general? No. And just to show you, there are two prominent examples for why it's not. One is ring opening polymerization, which we're going to talk about just briefly next time. So this is called a lactone, which is a cyclic ester, and under the right conditions, this will undergo polymerization by a process called ring opening polymerization, or ROP, and this actually proceeds by chain growth. Another prominent example is when proteins and peptides are made in biological systems. They also have a motif like this, where they're polyamides, and they are made by chain growth processes because they're actually catalyzed by enzymes. So, but this will never change. I can't think of a single example, although there might be, well, okay, and if I really use my creativity, I can think of some examples, but certainly not in this class, where you have all carbon atoms in the backbone. It always in our class proceeds by chain growth. There are some ways you could make materials like this by step growth, but we're not gonna worry about them. Okay, I had a few specific questions on the homeworks and old exams that were posted. So let's say the 2015 exam 1E, the PDI, or dispersity of a step growth reaction, is 1 plus the extent of polymerization, and this is on page 2.5 of the notes. 1I asks about the kinetic chain length. So the kinetic chain length is V bar, and it is given by the monomers added per second divided by the number of chains formed per second, and the per seconds cancel out, so the monomers added divided by the number of chains, that gives you the average degree of polymerization, and this is the rate of propagation over the rate of termination, rate of propagation with the seconds, rate of termination with the seconds. And under steady state, this is equivalent to, the steady state means that Vt equals Vi, so the rate of termination equals the rate of initiation. So this is due to steady state. And the kinetic chain length, if we use our kinetic expressions, or our rate laws that we derived in class, then we have the rate constant of propagation times the concentration of growing chains over 2 times the rate constant of termination times the rate of propagation. So what do we know based on the kinetics of the termination? What do we know based on the kinetics? Is that the chains should have this length. So this is the kinetic chain length. Why is it not just the real average chain length? Well, it's not the real average chain length because we don't know if the termination was by disproportionation or by combination. So, for combination, this is termination by combination. X sub n equals 2 times the kinetic chain length. But because combination has 2 chains that terminate by linking together to make one long chain. But termination by disproportionation gives you a number average degree of polymerization that is equal to the kinetic chain length. So in disproportionation, it's just that one of the polymer chains ends in a CH3 group, and the other polymer chain end with which it disproportionates ends in a double bond. You would be given this kinetic expression for the kinetic chain length. Okay, another question, how will branching affect the free volume? We covered this at the beginning. Branching increases the free volume. That's for homework 2, number 2H. Okay, this is a good question. Homework 2, 2F. So the question is, if the density of, and this had a polymer chain with some branching on it. And it asked, if you increased the density of the branched chains, what would that do to the energetic driving force for to go from a gauche state to a trans state? And what would it do to the ratio of gauche states to trans states? So if we look at the Newman projections for an unsubstituted chain, so no branching, we have our peace symbol, and B stands for backbone. So this is the backbone of the material. And this is the thermodynamically lowest energy state, because the backbones, which are bulky, are as far away from each other as they are possible to be. If we add a side chain, so if we add a side chain, oops, that is where I wanted to add my side chain. We had a side chain S. Then the side chain and the backbone in the trans conformation have this unfavorable interaction. So what we've done is made the trans state less favorable by adding the branch. So as a result, the ratio of gauche states to trans states with respect to the positions of the backbones will increase, because now the trans state is less favorable, or a little bit higher in energy than it used to be, because now in what used to be the nice trans state now has this unfavorable gauche interaction with the side chain. So what that's going to do is shrink the gap in energy between the trans state and the gauche state, and therefore increase the relative number of dihedral conformations that are in the gauche state relative to the trans state, because there's not as much of an advantage now to being in the trans state. That's a good question. Next question is about adding more back, so also adding a greater density of side chains along the backbone and its effect on order in the film. Chances are this would decrease the glass transition temperature. It would make it a less dense material. It would also probably decrease the melting temperature, but we're not going to talk about that yet in the course. And it would probably also decrease the degree of crystallinity, so the fraction of crystalline states versus amorphous states, because we have more randomness in the film. So more randomness, less crystalline, more amorphous, lower Tg, lower Tm, less dense, less strong, less stiff. Okay, so 2015 exam 1, there was a question about polyurethanes. We didn't talk about this, so polyurethane is formed in the reaction of an alcohol with a diisocyanate, and what you get in the end with this is a urethane linkage. So this is a urethane, and we did not cover this reaction, but because somebody asked, I'm going to mention it. The reason why this is interesting is because it follows step growth polycondensation-like kinetics, but strictly speaking, it's not a polycondensation because there's no small molecule that's condensed that leaves the reaction. All the atoms here are accounted for in here. So alcohol isocyanate gives you a urethane. So a diol plus a diisocyanate gives you a polyurethane in an AA-BB type polymerization. There's a question about exam 1, number 4C. In that example, we were supposed to use the question referred to the Flory distribution, and to derive the Flory distribution, I'm not going to ask you to derive the Flory distribution, but in the derivation of the Flory distribution, we needed the definition of x sub n in terms of p, which is the Carruthers equation. Now, it's true that in part C to that exam, we were no longer assuming a stoichiometric imbalance, because this only works in cases of stoichiometric balances. So a 1-to-1 ratio of AA and BB type monomers, or a, by definition, 1-to-1 ratio of an AB type polymer. And you can only ever have a 1-to-1 ratio of an AB type monomer because A and B are attached on the same molecule. Okay, I think that will just about do it. Please feel free to send emails to me or the TAs before the exam, and I hope you found this useful. Thanks.